This video will discuss the solution to question 21, which goes as follows. The circuit in figure 1 can only achieve stable oscillation if, and then a number of constraints on the ratio between RB and RA are given. To investigate what the ratio should be between the value of RA and RB, let's have a close look at the circuit first. So this is the oscillator circuit we're going to work with, and it consists of three parts. This is the first part of the oscillator, and we will refer to it as the beta network. It is a frequency selective network that takes in some input signal and then outputs the input signal with some phase rotation and some attenuation at the output. The second component is this one, but it is completely invisible to the circuit operation with regard to sustained oscillations because it is a unity gain buffer. The potential at VA is simply copied at VB, and it therefore just isolates the impedance levels between the output of the beta network and the input of the following network. This has no impact on the open loop gain. The final component is this one, and we will refer to that as A. An important remark that we should make with regard to this amplifier is that it is in an inverting configuration, and that means that the gain of that amplifier is negative the feedback resistor, so that's R5, which is our RB, over the resistor that connects to the input, so that is RA. And we will use this later on. Let's first have a look at the transfer function of the frequency dependent network. This transfer function will be given on the formula sheet, so you don't need to know this one by heart. Now, to sustain oscillations, it's important to remember that the Barkhausen criterion should be satisfied, which means that the open loop gain, if we will call it L, has to be 1. And since 1 is a real number, that means that the imaginary parts of this beta transfer function should completely cancel each other. And that imposes an additional constraint on the frequency of oscillation. So let's try to solve that one first. And if we then solve this for the frequency of oscillation, we'll get omega is the square root of 6 over RC. And since this is the frequency of oscillation, we will add a small subscript O to this omega. To understand what impact the beta network will have on our incoming signal at the frequency of oscillation, we can simply evaluate beta at omega O. And if we do the complete calculation, you'll get that is negative 1 over 29. Now look back at the Barkhausen criterion. The open loop gain should be 1, and the open loop gain in our case is A times beta being 1. That means that to achieve an open loop gain of 1, our amplification factor of the inverting amplifier should be negative 29. And the amplification factor of that inverting amplifier is negative RB over RA. So that will yield us RB is 29 RA.